Yeah, I think. So I just thought. Yeah. I just
People who don't need a final anymore. They just, we know everything by now. We don't need to book anymore. We're done. That's right, we're done. I know everything. All right. Good afternoon, and welcome for our very last lecture of the semester. It's amazing how fast things have gone again. And a couple of things. By now you should know that the final is on Friday, just a week from now. Pretty late, 5 to 8 p.m., and it's going to be in 106 Stanley, wherever that is. We'll find. Oh, that's Stanley. So that's one thing. I also plan a review session next Wednesday. I still have to check if we're going to have this room, but it will be from 6 till 7:30 like we did in the past. So I'm going to try to use the same room as this one here. Okay. Homeworks we're due, but we're going to post some extra problems on the website just for you for exercise purposes and let you play around with them. And we'll post some solutions afterwards. Probably Wednesday, Thursday, we're going to just post the solutions to those. Okay. Also, there's going to be all midterms and finals and things like that. You can definitely should have a look at those as well. Let's see. Project. Let me just get some notes here. Can we get the overhead camera? All right. Cool. I have to kind of push. There we go. So as I mentioned before, I think I was very impressed with how most of the groups did the project. I think you guys really took the right shot at it, used all the tricks in the book. And actually the best report actually used, I think, probably all the tricks in the book altogether into one shot. So I think there were two very different ways of approaching it. The first one is a noun technique, by the way. If you take an FIR filter, so you have, let me just draw a delay line. This is a simple case. You have multiplies here, multiplies here, multiplies here. This is simplistic, but typically what you would do is add them all together, right? And the order of how you add them together is, in general, people start from the first end here and then propagate towards the end. So you have your first multiply, you take the second multiply, add those together, you take the result, move it to the next add, and so on and so forth. However, there's one beautiful property that a delay has, which helps you to make this thing faster. Delay operator, let's call it an operator, has a property against any arithmetic function, which is basically a distributive function, which basically says the following thing. If I have delay, and then let's say an add or a multiply, whatever it is, this is completely equivalent to having the delays move over the add and basically take the add first, add the two numbers together, and then put the delay at the output. This is equivalent. There's no difference between the two. So this I can use to move delays around and change the critical path. This thing is called retiming. It's a very well-known thing. For instance, if you run synopsis, logic synthesis, sequential synthesis, it will do retiming automatically to a certain extent. Figure out if you can move the delays to change those things. So actually it turns out that if you do this on an FIR filter, actually what I could do is restructure the whole operation to get something like this, where you just take the input and you provide all the multiplies on the input, and then basically you have now the structure running in the opposite direction. You take a delay, you put an add here, you put a delay, and you put an add here, and this is the output. This is the input, and this is the output. So now you can see that where originally, if you would have long FIR, it would have a lot of adders in the chain here, which creates a long critical path. Here what I do is move the delays in between the adders. And as a result of that, I can nicely kind of cut down the critical path. So basically one add and a multiply. Okay? And in some sense, that's what a lot of you did. Maybe not realizing that this is something which is something can be structured and automated, but that's a lot of what you did. So, well, gee, there's too many adders in a row, so can we reshuffle them a little bit? And as you can see, obviously, if this is A0 and A2, they're basically the same, so I have to compute it only one time. And A2 is half of that. So I can actually simplify that set of multiplications quite nicely and save adders as a result of this. Now there's one more thing you could do, which was a little bit, was not clear 100% if it's within the rules. Nobody did it. I could have gone one step further. I could say, okay, assume that I can delay the output with 1 clock cycle. I'm not changing anything in the performance, but I'm just going to put some extra delay in. As I said, it's kind of on the edge of what was allowable, because you changed the response, because everything is now appearing 1 clock cycle later. But if I just inject the delay here, okay, at the input, I can do that. It's basically just saying my output is going to appear 1 clock cycle later. Now I can start retiming this delay, and for instance, make it pop up here. So I can actually insert another delay between your multiply and your add, which once again would reduce the critical path. This is called pipelining. You really now start overlaying different computation on top of each other. So it's on the edge. Would have kind of, was not clear in the definition of the project if this was allowed or not. But it was one other way to basically go faster. And you could even go further and put more pipeline there. But at some point in time, the delay of the register becomes the dominant factor. And then you don't gain anything anymore. Okay? So that was one way of approaching it, is really restructuring this thing very carefully. And as I said, a lot of you have really done this almost to optimal end. Basically, 2 additions in a row is what a lot of you came up with. The other part was to say, well, gee, I'm going to look at the multiply add structure, what I have here, which is adds and shifts, and really do a very careful manipulation of how I forward the data through it. So one option is kind of think carry safe. Move your carries in a different way. Instead of having your adders like this, now move the carries horizontally or diagonally, like we did in a multiplier. So in this way, you can actually play around with where your critical path is, and then in the end, I can use a carry select adder or carry look ahead adder. Not the traditional carry look ahead. A lot of you figured out that actually kind of this combination of select and ripple works quite nicely. For instance, you take an adder, you divide it in 2 blocks of 4 bits, or 4 blocks of 2 bits. You do carry look ahead on each of those, and then you ripple the carry forward. For a small adder, works really nicely. Better, I think it's better actually than doing a full Wallace tree in this case. A Wallace tree adder. Carry look ahead adder, which is the tree structure. Now you just do partial look ahead. You make the complex gates to fan in of 4, to fan of 2, and then you ripple through. It's a combination of ripple and look ahead, which is a very powerful scheme. A lot of people do this in companies. You look, a lot of microprocessors, that's what people do. There was one group that also considered the adders as basically said, well, let's do the same trick as a Wallace tree multiplier. Every adder is 3 inputs, 2 outputs. Can I restructure this whole thing to play around with that and basically have reduction? And that came out quite nicely as well. So a lot of really cool ideas, I think. And as I said, I saw you kind of use every trick in the book that was out there. And if you do a good job, you typically ended up with fairly similar results in terms of performance. It was very hard to make something which is a factor 2 better than everybody else. It's easier to be really bad than to be really, really good. At some point in time, it saturates out, and everything you try to do only gives you limited value extra. But anyhow, very nice job, and very pleased on how it all came out. And posters were good too, so we're all done with that. Okay. Any questions? Any questions regarding the rest of the semester? Yes. I have to just compile. I have all the stuff sitting there. Oh, by the way, I make sure that you mail in your PowerPoint slides to us. If I don't have them, that could impact you. So make sure you mail them in. But I'll probably try to send it around somewhere next week. I have all the things there. I just have to put in my spreadsheet and kind of combine it all together. And what you will get is some highlighted feedback on what we taught. Okay. All right. Let's see. Anything else? That's about it. I think anything that I can think of. So exam is going to be as usual. There's going to be 5 questions, but you have 3 hours. Covering mostly the later material in the class, but there's definitely going to be some harping back to the earlier parts of the semester as well. So it covers the whole thing. And don't forget your book. And for those of you who lost the book, you're still going to need it. Okay. Having said that, let's, I've shown that. So what I'm going to do today, kind of to wrap up, one thing we didn't get to in this semester, somewhat of a pity, but you will have ample opportunities to learn more about it, is memory. We talked about registers, but we haven't talked about big memory blocks. And if you look at a modern microprocessor chip, about 80% of the chip is probably memory. If you think about large systems, of memory is an important part. If you think about the cost of your iPhone, it's about $100 for 8 GB of flash memory. That's a nice piece of money. So a big chunk of the systems really are storage. So memory is important. It's not that you make a lot of money out of that. Right now, memory business is not very good. Now, all the companies making memory are kind of on the edge. The price of memory goes cyclically, and right now they're at the bottom. So it's cheap to buy memory at this point in time. But anyhow, we haven't talked about it, so I'm just going to give you a glimpse on memory today. And then I'm going to wrap it up a little bit with kind of some discussion of where I see what I see happening in the next 10, 15 years. Definitely for those of you who want to make a career in design of integrated circuits, it's a good idea to kind of say, hey, is this something that's still going to be here 20 years from now, 30 years from now? Because obviously you're not going to retire soon, most of you. So it's worth to think a little bit about that. What's going to happen with that industry? What are the opportunities? Okay, so let's talk a little bit about memory. As you know, there's actually a lot of memories. If you talk about memory, there's many different types of memories. Every processor somewhere, anything when you really need very fast random access. Random access basically means that I have a memory block and I have address, and I can basically randomly access every cell in the memory in a row. Sequentially. I can say I go here, I go there, and so on and so forth. That's what's called random access memory. There's no ordering in the way you have to access a memory. So there's two major types of random access memory that people play around. There's actually three. One of them we call SRAM. Oops, let me just change that. Okay, well. SRAM stands for Static Random Access Memory. And there's another major type which is called DRAM, Dynamic Random Access Memory. And the difference between the two is trivial. We already know it. We already discussed this. Two ways of storing information. As we discussed in registers, one type of cell uses capacitance to store the value. The other cell uses positive feedback. It cross-coupled inverters. So SRAM is static, which means that if I keep the voltage intact, my data will remain stored in the cell. I don't have to do anything. I write something in a memory in an SRAM cell. I keep the supply voltages on. It's going to stay there. If I remove the supply voltage, obviously I'm going to lose the value. Okay? DRAM is based on capacitance, which means it leaks. You store an amount of charge on the capacitor. That's a 1. No charge is a 0. Okay? Now, if you know you put capacitor, you put a charge on it, it will leak away. So the time that I can store the data is limited, unless I refresh it. What I do is if I have stored something in DRAM, and those computers these days, you know, every meaningful laptop these days, what do you have? About 2 GB of DRAM or something like that. That's kind of the typical 1 GB, 2 GB of DRAM. That's where you store, basically, this is used as the main storage of your machine while it's running. The SRAM is used as cache. That's the fast access to the computer processor. Because there's a big difference between the two. DRAM is simpler. It just only needs a capacitor and a transistor per cell. So you can put a lot more cells in a large dense area. But SRAM is faster. So you put SRAM close to the processor. That's what the level 1 cache is, level 2 cache, level 3 cache. Very often they're all in SRAM. And then the DRAM is basically to store your programs. You basically, when you load a program out of your disk, you put it in a DRAM. Okay? So that's the main differentiation between the two. Now, for a long time, these were the key memory components. I think if people talked about memory, this was either SRAM or DRAM. However, over the last couple of years, we've seen a phenomenal growth in the third area, which is called non-volatile random access memories. This have been around for a long time. They have different names, EEPROM, EEPROM, but most recently, the one that's really successful is called flash memory. It's non-volatile memory. It's like it's random accessible, but rather than losing the data when you turn off the supply, a non-volatile memory keeps the data stored. So that's why it's called non-volatile. And the growth of flash has been amazing. It was invented in 1990 approximately. By the way, one of the first proposers of flash memory was here in Berkeley, was Jaemin Hu. Professor Hu basically was one of the co-inventors of flash memory. So today, the size of a flash cell is getting actually almost smaller than a DRAM cell. Same size approximately. So you can put huge amount of memory on a small silicon area, and you stack some die on top of each other, and that's why I get my 8 gigabyte, 16 gigabyte flash memory size that you can basically put in your iPhones and your iPods and all those kind of things. So tremendous growth, mostly because it's driven by this world of multimedia, audio, video type of applications. And the growth for this thing is still very strong. Okay. Now, what flash does is, I just don't have time to go through it, but I just give you the highlight of it. How do you create a non-volatile memory? Well, obviously what I should be able to do is change something in the cell, which is not going to stay there, which is going to stay there when I turn off the supply. And there's a couple of tricks you can do. For instance, one trick you can do is move the threshold of a transistor. So suppose I have a cell where I say, okay, if I have the capability, let's say I take a cell might have a capacitance and a transistor. Okay, that's one example. If I can change the threshold of that transistor, I might make it impossible to write into that cell, for instance. Because if I make the threshold very high, I'm never going to be able to turn on that transistor with a normal voltage. Or if I make it very low, it's always going to be on. It becomes a short circuit. So you can actually now program an open circuit or a closed circuit by moving the threshold of your transistors around. And that's really what most flash memories do. It's a transistor using programmable thresholds. And the programming of thresholds is done by a bunch of tricks, but it's mostly by trapping charge onto an oxide. Okay? So that's one way. But there's other ways of doing non-volatile techniques. You might have heard about SRAM. SRAM is ferroelectric. You use ferroelectric materials, and what you don't change is the transistor, but you change the resistor. Can I program a resistor to be large or small? And if you can sense the value of the resistor, I know if it's a 1 or a 0. Or you have MRAM, where you change the using magnetic properties to program a cell and change it indefinitely. So that's really this whole world of non-volatile memory. It's very successful these days. A lot of growth in that space. So these are the three main classes: SRAM, DRAM, and flash. Now, in most applications, typical system-on-a-chip designs, integrating flash is going to be very hard. Because as you can imagine, programming a threshold or programming a resistor requires some special materials. People use a variety of ferroelectric, piezoelectric, or even dual gate type strategies in flash. It changes the technology, makes it more complex. So actually combining flash memory with processing on the same chip very often is not a good idea, because it makes the cost go up substantially. So in reality, most of the people prefer to keep the flash memory on a separate chip, and then you smack them on top of each other using packaging strategies. Okay? Because of the cost of it really would drive up the cost of everything and yield and so on and so forth. Same thing is true with DRAM. The problem with DRAM, as I mentioned, DRAM is a capacitor, right? You put charge on the capacitor, and that's a 1, and there's no charge on the capacitor, it's a 0. Now, to make a good DRAM, I need a lot of capacitance. To make a good storage element, it's nice if the capacitance would be as large as possible. So making a large capacitor on a chip is not easy, because if I would do this on my traditional ways, the way I do design today, you would basically, let's say with the traditional process, what I would do is larger capacitors means more area. If I want to increase the large size of the capacitor, for instance, I can create a capacitor by taking a transistor and short circuit it, right? That's a capacitor. And I basically connect here, and I have a capacitor. Very nice capacitor because it's basically determined by the gate oxide. However, if I want to make it bigger, I have to stretch it out in a two-dimensional fashion. That takes area. We don't like that because what sells in memory is how many memory cells you get. Density is the most important thing in memory design. Above performance, above power, well, power dissipation is not really true. It's becoming an issue. But people always try to make the memory cells as small as possible. So in order to make large capacitance in a small area, what people have done is go three-dimensional. Like, for instance, what I could do is if I have a piece of silicon, I can etch a trench using basically a dry etching, plasma etching. I can make very nice trenches. You drill holes in the silicon, basically. And then you dump some silicon, some polysilicon in there, and some silicon dioxide, you go over it, and so on and so forth, and then you find a layer. And now I can see that my capacitance goes like this, and then go in depth. I really create a 3D structure, which gives me a lot of surface area for a capacitance, but at the same time, on the 2D space, on the chip level, it's very small. And if I put a transistor to access the thing, this transistor on top of the thing, you're done. Everything is sitting on top of each other. Very tricky, as you can imagine. Very different than your normal logic process. So again, if I would try to do very dense DRAM together with logic, it creates a much more complex process. The yield is going down, the cost goes up. So typically we don't put DRAM on a chip either. That's why you buy those SD DRAMs, like the ones that go in the back here. You get a new computer, you go to one of those websites, you get another gigabyte of memory, you get a little card, bingo, you plug it in, you're done. All right, so this is done separately. The only thing that really typically appears on a chip is this SRAM, because that's the fast access. Having this SRAM sitting very close to your cell itself, to your computational logic, is very important from a performance perspective. So that's why if you look at most chips, you will see big chunks of SRAM there. And SRAMs can be designed without doing very special technology tricks. It's really a design trick. Okay? So all those other ones are important, but I think from this class perspective, I think focusing on SRAM is the most important thing. By the way, there's some other memories that exist which are non-random access. Like, for instance, we have video memories. One thing about video is you have, let's say you take a video screen, and you write it row by row by row by row by row. It's very rare that you're going to randomly access a video memory. The data streams in, data streams out. So it's serial access, sequential access. So random access doesn't make that much sense. So fast video memories typically will have a far less complex addressing scheme, and as a result are simple. FIFOs are, it's really a FIFO, first in, first out type of structure most of the time. There's some other things, but for the sake of time, let's not talk about those. So the most important thing is really for chip designers that do logic is to focus on SRAM. And that's why it's worth spending some time on SRAM overall and some of the challenges. So this summarizes what I said. SRAM is static. Data is stored as long as the supply is supplied. They're larger. Typical SRAM cells have 6 transistors per cell. This is called, for good reason, it's called the 6-transistor cell. There's also an 8-transistor cell, but that's futuristic. Typically, it's better to have less transistors because it's smaller. It's fast. So it's a good logic structure. DRAM, on the other hand, is based on a capacitor and a transistor. So this is your typical DRAM cell. It's called a 1T cell because you only use a single transistor. There's other versions that use 2 transistors. There's versions with 3 transistors. Might be a little bit easier to implement in a logic process because, as I said, here the key factor is how to make a large capacitance. Now we have diodes sitting here. This transistor leaks, so charge leaks away, so you have to refresh it. And refreshing is on a regular base, periodic base, when your memory is sitting there, when it's not doing anything. You read a word, you read it out, you decode it, and you write it back into the memory. That's what refreshing is replenishing the charge that was lost. You read, it leaks away, bingo, you read it again, you write it back, you replenish all the charge. Okay? That's just creating some overhead, obviously with DRAM memories. But as I said, there's a lot smaller than a factor of 4, 5, 8 more smaller than, let's say, a static SRAM cell. Okay. Now, let's think a little bit about memory design and what it all takes. It's kind of interesting to think about it, right? So we have learned about registers, so we know how to store something. But DRAM, we can do something more. Right? In a register, you have 8 bits, 16-bit, 32 bits. In a DRAM, I want to store 1,000,000 bits. Or 256K or something like that. So you have lots of them. And lots of them basically gives you some advantages. Right? It helps you to think about how can I make this thing smaller, denser, better performant. Because ultimately, a memory is a very regular structure. Logic is a mess. Right? You've seen this. When you have to lay out your adders and you have to connect the thing together, you get these wires all over the place. It's painful. While memory, you just put rows of cells and rows of cells and rows of cells, very regular, and you put a very nice regular interconnect grid on top of that. So everything is nicely structured. It's very repetitive. So from an analysis perspective, it's a lot easier too, because everything is the same, approximately. So I now analyze one, and I just keep on repeating the darn thing over and over and over again. So it's a very different game. And as I mentioned, the key focus here is on density. You want to make it smaller, as small as you can. And as a result of that, very often what you're going to do is say, well, gee, if I want to make it small, I can make things small, but I'm going to give up on something else. Maybe performance. I'm not going to be very fast. I'm not going to use big transistors because big transistors are expensive. Or I might give up on noise margin. And in logic, you put a lot of noise margin there because you want to make sure it goes over. In memory, you say, well, now we're going to be a little skimpier on the noise margin, and we're going to trade it off for density. And then we're going to put some tricks around, because it's regular, to make sure it always works correctly. Okay? So it's trading off reliability for density. That's what we do with most memories. Now, suppose now I have to store 1,000,000, say I want to make a memory which is 1 megabit by 8, organized in words of 8. So the first straightforward way of implementing this thing would be say, well, gee, I'm going to have 8 bits, that's a word, and then I repeat this 1,000,000 times. Now you can imagine the aspect ratio of a chip like that would not be very pretty. It would be a very long, skinny chip. Packaging that stuff would be hard, and putting it on a board is not a very good idea. So we're not going to structure memories like that. Typically, the way you structure memory is you try to make it approximately rectangular. So instead of putting 8 bits here, another 8 bits here, I put some of them in parallel. And I try to basically make this kind of a block structure. Okay? So that's typically the way we do this. And now, in order to create a 2D array to basically access the information, we're going to have 2 types of addresses. Obviously, to access a piece of data in the memory, you have to have an address. The address is where the memory is stored. So a memory block is addressed now by, if you would have a sequential thing, I can have a single address. I say this is 1, 2, 3, 4, 5. It's easy. Now, if I start stacking them in 2 dimensions, I need 2 addresses. I need the row address. I say at what row is it stored, and I need the column address. So a memory address typically will consist of a row address and a column address. And actually, if you have even bigger memories, we're going to split it up into multiple blocks, large blocks. instead of having one block of 10 million bits, we're going to have maybe 10 blocks of 1 million bits. So the third address we're going to need is the block address. What type of block do you live in? And then once you know the block, you can figure out the row and the column. Okay? So this is how memories look. So you have the memory core, which is m times n. And we have the row address, we have the column address coming in. Now, if I would have, let's say, again, if I would have a 1000 by 1000 memory, just an example, that's a million bit memory, it means I have 1000 rows in this direction, 1000 columns in the other direction, right? Now, the address I could do in pure binary format. It's 1 when you want to address it, 0 when you don't address a row. But that's a pain in the neck too, because 1000 for the row address, 1000 for the column, that's 2000 bits. You can imagine that it would require a lot of pins on your package. So rather than presenting address in pure binary format, we really use an encoded format. Well, actually, we use a binary representation. Because 1000 bits can be addressed by log 2n of 1000, that's a 10. 10 bits. I can actually, with 10 bits, binary encoded, I can select any one out of 1000 bits. So the first block you will see when the address comes into memory, the first thing you will see is what's called a row decoder. Something that takes your 10 bits in and turns it into 1000 bits, and out of this 1000 bits, only a single bit will be high at any point in time. Because obviously you want to only address one row at a time. And the same thing is true with the column decoder. Out of 1000 bits, I basically, of 1000 columns, I select one column. So the total address is now only 20 bits. That's a lot more manageable. Now decoders are basically giant arrays of NOR and NAND gates. Bottom line. Large, very complex NOR and NAND gates. You can choose how you implement it, but these are big fan-in gates. Like here you have 10 inputs, 1 output, and you have 1000 of those gates. That's really what a decoder is. And you try to make this as small as possible. Again, an interesting topic. Again, a topic I won't spend too much time on because I really want to talk a little bit about the memory cell in itself today. So, but you can see a memory emerging. Large array of cells, very densely packed with each other. And then on the periphery, I have the row address, column address. Some more nomenclature, or basically some more definitions to be aware of. So you have a cell here. So your row address comes in, you select one row, and you have a wire that basically goes high. That wire that addresses the cell in the horizontal direction is called a word line. A word line is this horizontal select line that will say, hey, you are on, you're off. Okay? Similarly, once I select a certain cell to read, I'm going to read out the whole row in one shot. So suppose I want to do a read operation or write operation. What we're going to do is read the whole cell or this whole row in one shot. So I get 1000 bits coming to the output. Okay? If I have 1000 by 1000. So I get one word line going high, I enable one row, all those bits come out. Those 1000 lines that come out of there are called the bit lines. The bit line, right here, is the data output of the cell. So the word line is the control, the select signal. The bit line is where the data appears. Okay? Now you still have 1000 bits coming out of there, and I only need one. That's where the column decoder then comes in. The column decoder can be considered as a multiplexer. I have 1000 bits in, I have 10 bits of control signals, and I want to pick one bit out of there. It's a giant multiplexer that selects one bit out of 1000, approximately. Okay? So that's kind of the structure of any memory you can talk about. Is it flash, DRAM, SRAM? They all are built around the same concept. Row decoders, column decoders, core array, word lines, bit lines. Okay? They're common. Okay? All right. So let's talk a little bit about SRAM. Let's ignore all the other memory types for the time being, and let's think about what it takes to build a good memory cell. Okay? Static memory, we know everything about it. We've talked about it when we talked about flip-flops. There's no difference. A memory cell looks like two cross-coupled inverters. And as you know, once they're in a certain state and you don't remove the supply voltage, we're going to be bistable. We're going to be either in the 1 position or the 0 position. Okay, and it's positive feedback. Now, remember what we did for the flip-flops. We said, well, gee, you know, in order to write in this thing, you have to be able to overpower it some way, right? Because this thing is in a certain state, and if you want to write it in a different state, you have to kind of force it to go from one state to the next state. And there's a couple of ways of doing this, but in SRAM, we have one particular way of addressing this. So this is what we did with our old strategy, right? It was a strategy we used for flip-flops. You say, I make one of those inverters kind of a little bit weak, make the other one strong, and then I force one state in there. I overpower that weak inverter. Okay? That's one way, but it's very hard because it's asymmetrical. Okay? So in memory, we're going to do something different in SRAMs. This is your typical, very famous 6-transistor SRAM cell. I think virtually any SRAM I know that's on chip today is doing this. A lot of variants on it, but it's always the same, exactly the same type of structure. At the core, we have our cross-coupled inverters. Okay? We have inverter here, and this is one inverter, this is a second inverter, and you cross-couple the inputs and the outputs. Now, in order to read and write into this memory, we're going to add 2 more transistors. That's why we call it 6-transistor memory cell. These are 2 NMOS devices, M5 and M6, which are going to be connected to the word line. Remember, the word line is that control line that comes in, selects a complete row. Okay? So when this is off, transistor of your cell is happily sitting on its own. Nothing is happening. It's isolated from the rest of the world. It just stores the previous value. Okay? So now, the bit lines, this is a symmetrical structure. So we see that for every cell, we're not going to provide 1 bit line, we'll provide 2 bit lines. We actually make it differential. We make it differential in the sense that every time you're going to have bit line and bit line invert. Because as you know, a flip-flop always has Q and Q bar. So you're going to use that to actually save power and make the cell smaller. Because let's see what's happening now. Suppose I want to write something into this memory block. What I'm going to do is I'm going to say, I want to put a 1 in node Q, and I want to put a 0 in Q bar. What I do is I put a 0 here. I put this bit line to 1. I force one side to 0, force one side to 1, and then I raise the word line. I turn the NMOS devices on. So now you see that I'm going to pull on this flip-flop from both ends. Right? I'm going to force one side, I'm going to try to pull this thing down, and on the other side, I'm going to try to pull this thing up and force it into that position. If you want to write a 0, you just do the opposite. You put a 1 here, put a 0 here, raise the word line, force the cell into a certain position. Okay? Now, second phase. Suppose I want to do a read out of a cell like this. What should I do? Well, remember one thing. Right? I have 1,000 bits on a column. Right? Normally we won't do that, but it's just an example. Typically I'm going to do less than that because 1,000 is going to be quite slow. But you can imagine that the structure, and actually I have it in the next slide. I'm going to come back to this. Now you can see that for a single column, I have my word lines coming in horizontally, word line 0, word line 1, whatever it is. And then you have your bit lines coming vertically. Okay? And then you stack rows in between, or cells between those. Now if you think about the capacitance on this wire here, that's going to be fairly large. Because this wire is going all the way from top to bottom. And every one of those access transistors is going to add diffusion capacitance. And some gate source capacitance to this as well. So you have 1,000 bits on our thing. You can say, let's say a femtofarad per bit. 1,000 times a femtofarad is a picofarad. Okay? So it means if I want to do a read operation, I have to be able to move that picofarad up and down. It's not easy. Right? And it's even harder because typically when I drive a picofarad, what do? I put a giant buffer in front of it. But I'm not allowed to do that because I cannot put a big buffer in every one of those cells. I want to keep them small. Very small. So I'm going to make all those transistors minimum size if I can. The smaller the better, because my cell gets smaller. So I have a giant problem, a huge problem at hand. I have this tiny little transistor that has to move that big capacitance up and down. So what can I do? Any idea? Any idea of how you can do that? A very small transistor move a big capacitor. That's a tough task at hand, right? It's not an easy thing to do. Any idea, suggestion of what I could think about? How can I make writing or driving a large capacitance easy? Or simpler, or faster? Remember the C times delta V over I? That's my propagation delay, right? That's all I can play around with. C delta V times I. Now, C is a given. Right? Well, I only can make smaller memory cells, and obviously you can do that. You say, okay, I'm not going to put 1,000 bits, I'm going to put 500 bits. That's one option. So C is a given. I is a given. Right? Because I have a small transistor. The small transistor tells me how much current I have. So what's left? Delta V. Remember these reduced swing thingies? That's exactly what we're going to do with the memory. So the way we basically read and adhere, and that's why actually those structures are differential, is before we're going to do a read operation, what we do is exactly it's a dynamic structure. We pre-charge both of your bit lines to VDD. Okay? You make both of them VDD, pre-charging. It's like a dynamic structure. You take your bit line, pre-charge it. And then I'm going to turn on my word line. So let's say that this is a 1, this is a 0. Okay? This is at VDD, this is at VDD. And then I turn on my word line. I turn on those two transistors. Okay? 1, 1, nothing will happen here because there's VDD on both sides. So that side happily stays at VDD. The other side here is 0. So what I have is my NMOS device is on. I have this access device, and I have my bit line. So those two transistors are going to start discharging the bit line. Okay? Not with a lot of current, because that's very small transistors. But slowly but surely going to take charge away from that bit line. Now, if I would have to wait for this whole thing to happen, I could wait forever. So that's not what we're doing. We say, okay, we have bit line 1 is high. The other bit line starts to discharge, like this. So rather than wait for this thing to go all the way down to 0, say, no, if I have a delta V which is large enough to detect, I'm happy. I know it's a 1 or a 0. So what we do is you take your two bit lines and you feed them to a differential amplifier called a sense amplifier. You take the value, the small difference, and after a certain time you say, okay, let's turn the amplifier on, and you amplify that small difference till you get it back to the rails. Okay? So this is exactly what we're doing here. It's a reduced swing logic gate. The bit line only goes over a certain amount. Once we have, let's say, 50 millivolt, so we're happy. Bingo, we turn on the amplifier goes and gets it all the way to 0 and 1. Okay? So that's the trick of memories. And we do this with all memories. Again, the trick of basically having a small transistor driving a big capacitor is to make it dynamic and let the swing be small. You only swing the bit lines over a certain amount of value. Okay? Very important trick, but a very useful one. Now you might say, well, by my goodness, this is complex, right? We know that dynamic, definitely those of you who did dynamic design in your project know it's not as easy as you think. There's a lot of things coming with it. So this is dynamic design. Isn't dynamic design, don't you have challenges with crosstalk, charge distribution, all this kind of stuff that comes in? So it's very hard. How can you make it work? Well, the beautiful thing about a memory is very repetitive. It's a very repetitive structure. So I can figure out all the capacitance that are sitting there. And it's always the same thing. It repeats over and over and over and over again. So you can very carefully analyze it and make sure that you're safe, that you don't have crosstalk things. You cancel out differential signals. You cancel out common mode signals. A whole bunch of things you do to make sure that you get a clean signal out of there. And the main reason you can do that is because it's always the same over and over and over again. In logic, it's a lot harder because every circumstance is different. Okay? So that's really how these things work. Write is you put the bit lines 1, 0, 0, 1, and then you force the cell into a certain position. And the read is you precharge your bit lines to VDD, and then you let one transistor, one side pull it down, the other one stays at 1. You amplify it, bingo, you have your bit out. Okay? Now, that bit precharging actually, start thinking about it. When you precharge your bit lines during a read, you start realizing, you look at the cell and say, hey, I look at those transistors. You start thinking about how should I size my transistors in my cell? How should I do that? And the first thing you observe is that from a read operation perspective, the PMOSes don't do anything. Right? I basically have one thing that sits there. The PMOS kind of keeps it high, because that's the PMOS, but it doesn't provide any current, just battles leakage a bit. It's the NMOSes that do all the work. Right? If you want to pull the load to 0, I'm going to have this access transistor and this NMOS device kind of pulling the thing down. So the PMOSes are just sitting there for the fun. Well, not really. They're basically canceling out leakage. If you basically put a memory in a certain state, what the PMOS is going to make sure is that the leakage is not going to make your cell flip. It's the NMOSes that really are doing the work. So that's why in a SRAM cell, you will see that the PMOS typically are going to be sized very, very tiny. They don't do anything. You might actually even make lousy PMOSes. In some processes, that's exactly what they did. PMOSes that are really tiny, you put them on top of the NMOSes on some extra polysilicon layers. You put them on top of there. They don't provide a lot of current, but who cares? As long as it's bigger than the leakage, you're fine. It's the NMOSes that you really make do all the work, and that you're going to size up very carefully. Okay? So it's an asymmetrical cell. Very different than what you're going to see in logic, where depending if you need a 0 or a 1, it's either the PMOS is driving or the NMOS is driving. Right? In memory, it's very different. It's asymmetrical. Okay? So that's basically the whole thing. So write operation, you just take the word lines, you put the values on there, and force them in. Halt is quite simple. If you don't want to address a memory cell, you just keep the word line low. Nothing is going to happen. As long as your supply voltage is there, it will stay there. And then the read operation is what I've just shown. You have one side which you keep high. You basically turn on the word lines. The one that is the one side, nothing happens. If there's a 0 stored here, we're going to discharge this node through this path here, this transistor, the NMOS of this device, and this NMOS device. We'll discharge this thing very slowly, feed it to a sense amplifier, amplify it out. Okay? Now, there's one thing that I would like you to remember. That's why I really got to this thing a bit. Because there's one simple trick that you have to be aware of. Or, no, it's not a trick, but a design trade-off. And I think this is kind of why I kind of threw this in. It's an important thing to remember. And having 141 without knowing this is kind of dicey, I would say. So let's think a little bit about what it would take to write a memory cell. Right? Okay. As I said, what I'm doing is I have a cross-coupled inverter pair, 2 NMOSes, and I put let's say if this is 0 and this is 1, I put a 1 here, I put a 0 here, and then I enable the word line. Okay? Seems pretty trivial, right? You put the values on the word lines, and then I turn on the access transistor, bingo, I write. Now, be careful though, because this is actually, there's still a battle going on here. There's still 2 types. If you look at this node, on one side I have the bit line trying to force a value into the cell, but at the same time you still have that inverter sitting there fighting it. And every time there's a fight, there's going to be some ratioing to be needed. Right? We've seen this in the past, right? When we did level restoring devices, we saw there's a feedback structure happening there, and if you're not careful, if you size the devices wrong, you might not be able to do anything. So the same is true here. For this to work, I have to make sure that this device can overpower the other inverter. It's strong enough to force it into the new state. Okay? So there's going to be very specific requirements on how to size the transistors if you want to make the cell work. It's ratioed logic, like we had pseudo-NMOS. Similarly, let's look at the other case. I do a read. Again, I have my inverters here. And I have my access devices. And I have two bit lines which are pre-charged at VDD. So this is 0, this is 1, and this is my word line going up. Right, so what I hope is that this 0 will be able to discharge that particular bit line. Right? So we're going to slowly but surely discharge it. But this is a big capacitor. Right? There's a picofarad capacitance here with a lot of charge. Now I turn on these word lines. For more practical purposes, I almost can consider this as VDD. Okay? So I have a 0 stored here, but I know turn on a transistor with VDD on the other side. There might be a chance that this VDD says, hey, no, if this transistor is too strong, I can overpower this node and pull it back in the other direction again. Right? Because it's not really VDD, but it's a big capacitor with a lot of charge. It looks like to me like VDD. So you have to be careful that you don't flip the cell while reading it, because that would be horrendous, right? I read it and bingo, I lose the data. So you have to be very careful. And again, as a result of that, there's going to be some transistor sizing requirements that come with it. So this is what it all boils down to. Nowadays, I think I can ask you now, hey, how should I size those transistors in such a way that it doesn't happen? And I think you should be able to answer this. We've done enough transistor sizing. We've done enough analysis, DC analysis of cells. So this is a problem that is perfectly legit for you to solve. Right? You should be able to handle that. And let's just look at the read case. Okay? See what's happening. So as I mentioned, I have two bit lines that sit at VDD. Okay? And then I turn on my word line. Now let's look at happen when this is a 1, this is a 0. It means from your two inverters, in the one case the PMOS is going to be on, and you can assume that that PMOS is going to be grounded, right? It's because it's on. And the NMOS on the other side is the NMOS is on and pulling that node low. That's the steady state condition. Okay? So NMOS M1 is on, M4 is on, and transistor M2 and M3 are off. And now I basically apply this and I raise the word line. When will the thing go wrong? What is the necessary condition for the cell to flip? That's what we have to think about. All right, so I have something which is VDD here. I have a node that's at 0. And now I turn this NMOS on and this NMOS on. So if I take this little circuit, I don't care about this one because nothing will happen here. Right? This node is at 1. I turn on the transistor. This is 1. No current will flow. Everybody's happy. So on that side, nothing is really occurring. It's on the other side that we're worried. Because here, as you can see, you have now, if I redraw this a bit, I have transistor M5 right here, and I have transistor M1, and that's my output. And this thing has a gate at VDD. And this is also at VDD, V out. Okay, so this structure should look familiar to you. Right? Remember it? Seen this way, way, way back, weeks and weeks and weeks and weeks and weeks ago. This is your saturated load NMOS inverter, which is a ratio device, as you remember. Right? The sizing of the transistor is going to matter. So suppose now that I make, I want to make sure that this node V out, what's the necessary condition for the cell to flip? Any idea? What has to happen for V out before the cell might start flipping around? Which we don't want to happen, right? We want to keep it in the same state. What's the necessary condition for V out? V out is supposed to stay at 0. What will make the positive feedback to kick in and maybe move the cell in another state. What has to happen with V out? It has to go up. How much? 50% if it really is a symmetrical situation. So V out has to become larger. Remember, this node connects to an inverter. For that inverter to flip, we have to basically make the input go higher than the VM of that inverter. So thing will go wrong if V out is larger than VM. Okay? Now, solving this problem is very straightforward. It's a DC analysis problem. We want to make sure that when we apply this W waveform here, that this node here will never go above VM. If it stays below VM, you're going to be fine. You remove the input, the gate is going to be perfectly go back to zeros and ones. So that's the necessary condition. Bottom line is that will only happen when M5 becomes fairly large. Right? If M1 is much larger than M5, the output will always stay very low. However, if M5 becomes quite strong, that access transistor, make that one strong compared to M1, we have a chance that thing is going to flip. So you actually can solve this. This is a pure DC solution problem. I write the current to M5, I equal it to the current to M1, and I basically solve it for the value delta V, or V out, basically. We solve it for V out and say, okay, V out has to be smaller than VM. Because if it will be larger than that, my cell might flip. And indeed, you can solve these things, and you can come up with some constraints, and you can see how the voltage rise goes as a function of the cell ratio, and the cell ratio is the ratio of transistor M1 over M5. So you can see that M5 gets stronger and stronger and stronger. Delta V goes up, and at some point in time here, cell fails. So we have to make sure that M5 is weaker than M1 with a certain ratio. Not much. Actually, for a traditional 90 nanometer process or whatever it is, it's about a factor of 1. If you make them approximately equal size, you're going to be fine. Or maybe make M1 a little bit larger, but not by much. So that's the first constraint, a very important constraint when you do design of those cells. Same thing I can do for the write operation. Similar analysis. In the right condition, what we have is the following thing. So I have a cell where on one node I have a 1, another node I have a 0, I want to force this to 1, and I want to force this to 0. Okay? So that's really what we have to be able to accomplish. We have to be able to pull one node high and the other node low. So again, we have the same problem here. If you look at this structure, now we can write actually equations for both sides. You look at this structure here. Again, I have now a gate, which is a PMOS, which is grounded, and I have an NMOS connected to ground as well, and this is VDD, and this is V out. Okay, so we can recognize this structure. It's a pseudo NMOS inverter. You have a PMOS load, which is grounded, and you have an NMOS pull-down device. Okay, so again, a known thing we can solve. We can write down the current equations, and in this case, for the cell to flip, if we want to make sure that we can flip the cell, we have to be able to pull down this node below the VM of the inverter. If you cannot pull it down low enough, we're never going to make the thing flow or flip. So in this case, we have to make sure that V out of this inverter is smaller than VM of the inverter. And again, I can write down my current equations, and I'm done. And I can do the same thing on the other side. Here I have to make sure that this node consists of M5 and M1 goes higher than V out. Okay? So this is a PMOS constraint. This is an NMOS ratio constraint. I can write down the expression. All of this expression, I can basically solve my requirements on my transistor. Now, those of you who have been watching very carefully at what I just said, say, hey, wait a second. This is not possible. Right? If I look here, look at this structure. Forget about this one here. forget about, look at this side. This is the same structure we have analyzed for the read operation. And exactly the same thing. You have the NMOS device in saturated mode, and you have the other NMOS basically pulling down, and we have V out. It's exactly the same structure what we had before. There we said that in the previous case, for a read operation, we have to make sure that V out never is going higher than a certain value. And here we say in order to write a 1, I have to make sure it goes higher than Vm. We have exactly the same condition but reversed. So this is non-solvable. Still, this thing works. Why? Well, it's feedback, right? In this case, actually, this doesn't matter, because if I can make this node to flip around, if I can make this thing force to 0, at that point in time, the feedback comes in action, and this doesn't matter. It will make the thing move. Okay? So we have to be very careful with those conditions, because they might look bizarre, because, hey, this is one way, the other way, this way. So what's going on here? So with sizing, SRAM is very important. Basically, making sure that the cell is small and that it still works is very crucial. And this is a simulation again of the right condition. In this case, we only look at the PMOS case, and you can see that for, if the PMOS would get too strong, we will basically get a cell voltage which is going to 0.4, and we're basically toast again. Let me screw that. So this is typically how it would look like. This is a typical 60 SRAM cell layout. You can see it's fairly intricate. Designing a thing like that, it looks simple, but since you've done some layout now, you know these things are non-trivial. Trying to put something together with this density requires a lot of very careful playing. Actually, sometimes it requires cheating. Actually, most SRAM designers cheat. The way they do this is, well, there's some design rules that says I cannot put this thing too close to it, but nah, I know it's going to work. If under a certain condition, I'm going to analyze it very carefully, I'm going to violate some of the design rules. I'm going to put things closer than I should. Or very often, if you look at the most fancy designs, they're going to do very interesting things. They're going to have like contacts which are hexagonal. They cut off the corners, because then if I cut a corner, I can put something closer again to it, and I can compact everything a little bit closer together. Now, this is not something you do on a Sunday evening. It really requires a lot of effort. Designing a good SRAM cell that's really tiny takes a lot of effort. And it's very important, as I said, because 80% of your chip might be SRAM. So saving out a little bit here and there has a big impact on the cost of your chip. So this is the job of a SRAM designer. It's really very tiny, trying to compress everything together. And as you can notice, it's 6 transistors, but there's actually quite a bit of contacts in there. Sneaking in those contacts is not easy, because contacts are fairly large, and they kind of almost dominate the area. So a lot of thinking goes into that. And you see companies, I once saw pictures like, say, Texas Instruments. You look at what they do from generation to generation. Let's say you look at 380 nanometer, 250 nanometer, 180, 90, whatever it is, and you see the evolution of their cell over the ages. And typically they don't change very much from technology to technology. But then occasionally they find a new trick, change a little bit in the process, and then they get squeezed off a little bit more, just to make the cell smaller. And they occasionally make some changes in the process to make these things happen. Because as I said, this is important. But anyhow, this is what it looked like in real life. This is a memory cell. This is a 65 nanometer SRAM cell from Motorola, Philips, and ST as part of the, was part of the Kroll Alliance type of design. You can see it's pretty tricky. It's very dense, and you can see with all the lithography effects, some of those wires that you think are nice thick wires and contacts really get very skinny. They really push very carefully on design rules and still get meaningful transistors, because, those things are getting very small, very skinny. And you still have to make sure it works correctly. Anyhow, so that gives you a kind of a glimpse on memory design. It's very short. I could actually go on for 10 weeks talking about memory design. I'm not going to do that. 241 actually spends a lot more time on memory We talk a lot about flash memories and non-volatile designs and decoder designs and sense amplifier designs and all this kind of goody stuff. But that's a little bit beyond the scope of this class, so don't worry too much about that. But I think it's important at least that you have a sense of where memory design fits and how it's different than logic design. Okay, that's important. That's why I really wanted to kind of bring this in, even though I only had limited time to talk about it. So, other work to be done. Actually, there's some very interesting timing issues as well in memories. Like, for instance, sense amplifier. Amplifiers, for those of you who've taken 105, just take 140, you know that an amplifier to work, you have to have current flowing through it. Now, can you imagine those amplifiers in there burning current all the time? That's a lot of power. We don't want to do that. So sense amplifiers, we're only going to turn on for a very short time. You apply the word line, the bit starts to kind of drift, the bit line drifts downwards, and then we know if enough delta V, then we say, okay, now turn on the amplifier, amplify the signal, turn it back off. So we don't have active power dissipation having in the sense amplifier, only for a very short window of time. That requires very careful timing. Because if you're too early, you measure the wrong signal. If you're too late, you spend too much power already because your bit line is gone down too long. So you don't want to have that happen either. So a lot of interesting things, design issues, a lot of room for innovation. And that really brings me to the last part of this semester. I have 10 minutes, so I can kind of do some kind of crystal ball gazing. Well, it's not crystal ball gazing. Actually, it's pretty well now. So if you think about digital technology, where are we today? As we mentioned a bunch of times in the lecture, 65 nanometers is what most fabs will offer you. You go to TSMC, you go to IBM. You know, the run-of-the-mill process these days is 65 nanometers. Everybody kind of moved to that. State-of-the-art designs are now being shipped in 45 nanometers. If you think the latest parts from Intel and things like that, 45 nanometers is the technology of choice. So 45 nanometers is an absolute given. Pretty soon you will see 45 nanometers from all the major fabrication houses. TSMC has already process running, but it's not yet at the state of, it's not yet kind of the traditional production process. But 45 nanometers is happening. Intel is already doing 32 nanometer design. There's actually a bunch of, most fabs already are playing around with 32 nanometers. So 32 nanometers will be there. No doubt in my mind. Beyond that, it gets a little trickier. Latest I hear, and as I said, this is crystal ball gazing to a certain extent, because I've seen too many wrong predictions in the past, where people said, I can remember saying somebody there's going to be no design below 1 micron. And then somebody said there's no design below 300 nanometers. And then there was one that said, you know, around the 100 nanometer, you're totally toast. We're never going to be able to do lithography. We're not be able to manufacture this thing. Nowadays, we know we can build transistors with a channel length of about 5 to 8 nanometers. People have shown it. There's working transistors with 5 to 8 nanometer transistor channel lengths. So we can do that. The problem is, will we ever do it? That's a very different question. Today, when I talk to the different companies out there, there seems to be a consensus that 22 nanometers might be it. That, yeah, we'll do 22 nanometers. Beyond that, it's questionable. Actually, it's not clear anymore if you still gain. Right? Why do we do scaling? Remember that way back we said, why do we do scaling? Well, scaling is a cost issue and a performance issue. With scaling, I get faster transistors, I get lower energy, and the transistor cost per transistor goes down. So in my mind, it's very clear now that if you go below 32 nanometers, you won't gain very much from an energy perspective. You won't gain very much from a performance perspective. You still might get something from a cost perspective, but that's not clear. If it becomes so expensive to build those things, at some point in time you say, oh, gee, is it still worth it for me? Might the cost not start to go back up if you make them smaller and smaller and smaller? So we really have another 3 generations of technology scaling right in front of us. There's no doubt about that. Below that, it's going to be questionable. So you say, well, gee, I'm starting to worry about this thing right now, right? This is going to be the end of the famous Moore's law, right? This form, and probably yes. I think we're not going to keep on scaling. Ultimately, going below the size of a molecule won't work anyhow. Right? So, and physical effects start to come in. So below 3 to 5 nanometers, it's going to stop anyhow. So what does that say? Well, there's two things that are happening. And I think they're actually good for designers. I think this is the ultimate opportunity for design. Because what happened in the past? I'm working for Intel, and what do you do? Well, you have processor A, and I say, okay, now I want to make a new product. What do? You don't do anything. Well, very little. You say, okay, I'm just going to go and wait till a new technology arrives. I port processor from technology A to B to C to D, and boy, it gets faster, it gets smaller, it gets lower energy without doing anything. Well, 1,000 designers. Don't forget about 1,000 designers trying to do this, but that's a different note. But you basically get the improvements mostly from the technology. And what you do as a design house is introduce the things to deal with the weird stuff that happened with scaling. Right? Suddenly crosstalk is an issue. Suddenly resistance is an issue. Certainly that. So you start thinking about those things and model it and analyze it, and you redesign things in such a way that you deal with those things. But bottom line, if you look at the Intel microprocessors, from way back to now, they haven't changed very much. It was a nice model. You basically have, I have this, well, maybe add some extra concurrency and do things like that and make the cache a little bit bigger. But ultimately, fundamentally, very little has changed because you have the advantage of scaling. So suddenly now we say, well, gee, scaling might not help you that much anymore. Maybe there's an opportunity to say, well, maybe we should spend some time on design optimization, something we didn't have time for and you didn't want to do, because why should I spend a lot of time in design optimization if I automatically can get it from scaling? The fab will give it to me. So that's really what's happening now already, is that design optimization, cleverness in design creativity is becoming more and more important because of the fact that you don't get this freebie. Well, not a freebie, $10 billion is not free, but see what the fact is that now you can make a differentiating factor as a company in reducing cost, getting more performance, and all this type of things by basically thinking about clever design. And that's why I think designers are only increasing in value these days as a result of that. The fab is not the only solution anymore. It is really this combination of what's going to happen with technology, with what can I do. And I see this happening, and a lot of companies start realizing that. They're basically changing their business model. In the past, every company, if you want to be a semiconductor company, you want to be a big guy, you have to have a fab. Right? All big guys have fabs. That was the idea. Right? So the bigger the fab, the better. Right? That shows that you have a lot of macho, you're basically running the place. Today, the prediction now is that about 5 years from now, there are probably going to be 4 or 5 companies with fabs. Intel, IBM, TSMC. This for sure. Maybe Samsung. Samsung is making memories, so they're going to have their own things as well. So 4 fabs. And all the other companies, well, might have a little small fab in the background to do some weird stuff like RF and analog stuff and mixed signal things, which don't require these very small transistors. But all the digital design is going to go to this thing. And all the other companies really have become what is called fabless or fab light. These only have a small fab, fab light. So you see companies like Texas Instruments used to spend a lot of money in technology development. So that's done for us. We're going to focus more on the design added value. National has done this a long time back. You see it happening all over the place. In Europe, NXP got out of the fab place. Freescale is totally out of fabs. Basically, so more and more semiconductor companies saying, we're going to focus on design. That's where our value is. We're going to be creative, create new applications, new things, by thinking about architecture, how you optimize your design, and so on and so forth. So I think this is a tremendous opportunity. This is really the time that designers will shine, and where they're going to make the big differentiator than rather, hey, my fab is faster or better than yours. Because everybody's going to use the same fabs anyhow. So the differentiating factor is going to be smaller. And it's only a company like Intel, which is really a vertical integrated company, where they go all the way down from technology and use the technology to drive architecture. It's the only company, I think, that still will do this vertical thing. All the other ones will be far more horizontal. The fab is here, designers are here, system is here. So some important changes there, but I think it's exciting. The other thing that might happen, and is going to happen as well, is if you now start thinking about these technologies, you have memory technologies, you have RF technologies, and more we start putting all that stuff together, right? We want to make it in our cell phone. It has to be all fitting very nicely together. I want to get a lot of computation. I want to have radios. I want to have nice user interfaces. And it has to be very small. So all those technologies bring together. We're not going to put these things on the same die. So the other thing that's happening beyond the fact that we're probably going to saturate out on technology scaling is that we're going to leave the 2D area. Today, most chip design is done. We're basically designing a lot of transistors on a 2D plane. It's a little bit 3D. There's some stuff up and down. There's some wiring, things like that. But typically, you have only one layer of transistors. Once you get stuck, however, in the 2D space, what we're doing is clamping them closer and closer together. Suddenly, it's that we cannot make them closer anymore. The only escape is to go vertical and start thinking about, well, why not have chips and put a chip on top of it and put a chip on top of it and put a chip on top of it? 3D. And we're already doing it. If you take your cell phone, open it up, actually, even simpler, take a flash memory thing. They're cheap, right? You get them for free, basically. Open it up and look in there, take the plastic away of the packaging, and see what's happening. And you already see that they're stacking die on top of each other in those things. And they connect them together with wires or little bumps of solder or something like that. So that's already happening. But what you will see happening in the future is that those things will get closer integrated. There are going to be ways of stacking dies a lot closer together and connect them together in a three-dimensional fashion. And this way, you could have, for instance, this could be a digital chip. This could be a memory chip. This can be an RF chip, and so on and so forth. We can use different technologies for different solutions and then bring it all together in a very dense fashion. And that's probably the way I see an evolution happening in the way we're going to design things. So this opens the door for many new ideas, right? Because now suddenly I cannot wire just anymore like this. I can go like that. And I can start thinking about maybe I can redesign FPGAs, because now I can put the memory and the crossbars on top of each other, and I start thinking three-dimensional. Right? It's not easy, because we're used to two-dimensional thinking. It's like Star Wars, where you go from two-dimensional chess to three-dimensional chess. It's a lot harder when you have to start moving in a three-dimensional space. So, Star Trek. So it's a challenge, but it's an opportunity as well. So I think, bottom line, I believe there's tremendous opportunity still and to be had in the next 50 years in digital design. So that's really where I wanted to end. Just give you a little perspective. Hope you all had a good time this semester. I definitely did. And I would like to wish you success in whatever you're going to do next. Some of you might go to grad school. Some of you might actually get a job and start doing this type of stuff. So good luck, and we'll see you next week.